Hi, and this is Sean Perry. Welcome back to a video series made for MAT 1033 Intermediate Algebra. This will be video 6, an introduction to exponents. So first, let's remember what we're doing when we're doing multiplication by whole numbers. We thought of this in previous videos as adding a number to itself some number of times. So just as an example, remember that we have something like 5 times 3. We could see this as 5 groups of 3, 5 times that we add 3 to itself. And we'd get 15, of course. Notice that it doesn't matter how we interpret this as being either 5 groups of 3 or 3 groups of 5, right? If I consider 5 times 3 to actually be 5 plus itself 3 times, I still get 15, not 5 for some reason. So now let's consider doing the same thing again, but with multiplication in place of addition here. So I'm going to give an example of 5 to the power of 3. We sometimes call this 5 cubed or 5 to the third power. But notice that the 3 is small. It's tinier than the 5. That's to show you something. It's in what we call the superscript. It's in the upper right-hand corner. And what this tells me is that we are doing 5 times itself 3 times. 5 times 5 is 25, and 5 of those is 125. So we call this exponentiation. The little number up top is called the exponent, and the bottom number is called the base. So now let's do some critical notes. Copy this part. I want to see this on paper for you to get credit for the video. If I take x to the nth power, that is x times itself n times. That's how you can think about whole positive exponents. It is the number of times you're multiplying x by itself. X to the first power is just x itself. And though it might strike you as a little odd right now, let's just call x to the 0th power 1. We'll see later on when we dive deeper into the algebra of exponents why that is in fact the case. But for right now, I just want you to get it through that anything to the 0th power, we're going to treat it as 1. Okay, so let's do some practice with that. Here we have an expression x times x. And using exponents, another way that we could write that is x to the 2nd power, x to the 2, or x squared, as it's sometimes called. Here is another example. Now here I wanted to make sure that what we're considering is 2 terms, 3x squared, and 2x. If I multiply those two together, well, multiplication can be done in any order. So let's consider the coefficients first. This is 2 times 3. And then we'd have x squared times x. Now, if I have x squared, that's just x times x. So x squared times x to the first, that's x times x times x. That's 3 x's. So we really get, when all the dust settles, 6x to the 3rd power. And let's just reflect on what that pattern might tell us here. If I multiply 2 terms together, I had the product of their coefficients up front, and I had the sum of their exponents, because that says how many times we multiplied by x. So let's identify a shortcut here. When we're multiplying terms, you multiply the coefficients, we add, and we add the exponents. So we can apply some of this formalism to distributing and factoring. Let's try these. Let's consider if we took x and multiplied that by x plus 3. Well, what would we get? So bringing x inside, we'd have x times x here. X times x is x squared. And then we'd have 3 times, well, the x again. So we usually write the x's second, and we would write this as 3x instead of x3. Now let's consider this sum. Now these aren't what we would call like terms. They have different powers. We'll talk more about that in just a moment. But for right now, I want you to notice that even though I'm not going to add them together, I could factor out something from each of them. Now, this is x times x. This is x times x times x. And so they each have at least 2 x's multiplying in each one. So what I could actually do is bring out x squared. I could divide x squared from each term because they each have at least x squared inside. Now here, I would only have a single x left. What would I have here? Well, we divided something by itself, so I would have 1. recall from the last video, right? If you factor out something completely from this kind of sum, you're going to need a 1 there to hold place. And you could think of that as being because if I was going to reverse the distributive property, I better get what we started with. And that means bringing this back inside, I need to get x squared plus x to the third. So we need that 1 there to hold place. And x to the first times x to the second is x to the third. So now let's talk about that term I mentioned, no pun intended. If we have two mathematical terms that have the same letters and at the same time the same exponents, these are called like terms. And like terms are special because we can add and subtract them to one another. We can't really add and subtract things that aren't like terms. And in fact, those can be added and subtracted to each other just by using the coefficients. So here's an example. Let's add these 4 terms together. We have the ones that I've color-coded in blue. They have x to the first, y to the second. They are like terms. We have the ones that I've coded in green. X to the third, y to the first. Those are like terms. If I combine the blue ones, I combine their coefficients. 2 plus 4 is 6. And if I combine the green ones, 3 and then minus 2, remember the minus sign attaches to this guy that's right to the right side of it. Minus 2, that's 1. And so this says 1 x to the third, y to the first, right? The 1 is both invisible in the exponent here and as a coefficient here. We generally don't write to the first power in the exponent, and we generally don't write times 1 up front as a coefficient. Now that's combining the terms. What if I wanted to factor this, just for fun? So we could look at each one and say, well, they at least have 1 x apiece. This one has an x and this one does too. This one only has 1, so that's all I can pull out. And this one has a y squared, but this one only has 1 y. So I could pull that out too. I could pull a single y out front. And let's see that this is actually done correctly, right? In fact, I see a mistake. If I factor out a x from this one, the first term, there's no more x's because I would want to put this back inside. I would only have 1 of them. I would have y squared. Here I've made a mistake because, yes, I could bring out an x, but I could only bring out 1 x and there were 3 inside. So if I wanted something to hold place here, that if I multiplied it back inside would give me x to the third, well then it's an x squared that better be there, yeah. Okay, so this would be factoring that expression after combining like terms. So now let's go back to considering the exponentiation of numbers, right? Does order really matter, right? 2 to the third or 3 to the 2, does it matter who's in the superscript? Does it matter who the exponent is? Well, let's take a look at an example. If I have 2 to the third power, that's 2 times 2 times 2. 2 times itself 3 times. That's 8. But if I have 3 to the second power, that's 3 times 3. 3 times itself twice. Now that's 9. And those two numbers are not the same. So interchanging the role of who's in the exponent and who is the base is not going to give you the same number. And that means that order matters. We say then that exponentiation is not commutative. The order in which you do it actually matters, as opposed to multiplication and addition. Now that might strike you as a little weird because multiplication was just addition repeated, and it was commutative, and so is addition. And now I've done multiplication repeated, and yet it is not commutative. That is not a commutative operation. It matters how many groups we're talking about times themselves, right? So we have to keep that in mind as we go forward. Something about exponentiation is a bit more complicated than the first two. It is no longer order independent. So you can plug this into many calculators. There's a symbol for that. Call this a caret. And we would write 4 to the third power as 4 caret 3, or 4 to the third. And 4 times 4 is 16, times another 4 is 64. So it's good to know how to put this in your calculator, but you must be very careful with negatives. When you are writing negatives to a power, I encourage you to always use parentheses. Truly, it only matters for even powers, but don't rely on that. Just use parentheses whenever you are exponenting a negative. Take the whole minus 3 here and stick it in parentheses, because that's the only way your calculator is going to do minus 3 times minus 3 to give you positive 9. Notice that if I do minus 3 to the second in your calculator, what it will usually give you for most calculators is minus 9. And that's because it interprets minus signs as times -1. And we'll learn later in the order of operations video that timesing happens after powering, after exponentiation. So 3 to the 2 gets done first, and then it slaps a negative sign on the front, which gives you -9, and those are not the same number, right? So if you want to get a number squared, you need to put that number in parentheses if it's negative, or you're going to have a bad time. You're going to sometimes, for even powers, get these two different answers, and that's no good. We want to get one answer, the correct answer every time. So parentheses. Okay, remember, to get credit for this video, you have to copy the notes and do the exercises. So try these exercises. Pause the video now. All right, let's take a look at how you did. So -2 to the third is -2 times -2, which is +4, times -2, which brings us back to -8. On the other hand, -2 to the 6th power, well, if I do 2 times 2 times 2 times 2 times 2 times 2, 6 times, I must multiply 2 by itself, I'll wind up with 64. And if I do -2, well, each one of those pairs of -2 cancels to a positive. So this even power is going to make this overall positive 64. Let's distribute, right? Bring this in against both terms. That's the exercise here. 2x squared times x to the third. Well, x squared is 2x's times x to the third. That's 3 more times x's. So that gives me a total of x to the 5th power. There's a 1 here, so I hit that with the x to the third, and I just get x to the third. So this is our final answer. Finally, let's do a little factory. I have 6x squared plus 8x to the third y. I'm going to pull a number out in addition to x to the second. So there is a number I can pull, both 6 and 8. They're both even. So I could pull a 2 out of each one. Now, if I do that, the number inside that needs to hold place is what? It's going to be a 3. Right? If you brought this whole thing back inside and multiplied it here, you'd get 6x squared, what we started with. So 3 is the right thing to put in this position. And then you have 8x to the third. Well, I need an x here, right? I'm going to hit this with an x squared, and it's going to need to give me an x to the third power. So there needs to be one more x here, and I need a 4, so that we have 2 times the 4 to give me an 8. All right, that's that. Thank you for your patience. Good luck with your studies, and I will see you in the next video.